Good morning, class. Today's lecture, I want us to look at stresses associated with all the forces that we've been calculating. The forces being stresses associated with all the forces that we've calculated, being the tensile stresses, ST, which is tensile stresses. Obviously, it's the tension force, applied tension force divided by your cross-sectional area, it's T over A. Then you've got compressive stresses, and which is your applied compression force divided by your cross-sectional area. Then we go to shear stresses, I would say V over A. V stands for shear over your cross-sectional area. These are just direct stresses. I don't go like this one. I don't want to go into details because it's not only these stresses. You can work out the distributed stresses over the entire section, but let's not go there. We're gonna just go to the direct stresses due to shear, and then we'll go to bending stresses. Which is M over Z. Z being section modulus. Where your Z is equal to I all over Y. If your IXX or your IYY divide by your Y lower or Y upper, depending on where you are calculating your stresses. So if you can take this and substitute in there, so your bending stress is going to be your M divided by I all over Y, which is M times Y divided by I. So depending on how you want to approach the question, if you like, you can calculate Z on the side, and then you say is my applied moment. You know how to calculate moments. Is my applied moment divided by Z. But there's an equation that we use for calculating that, for calculating the bending stresses. Let me just quickly look at that equation now. Bending equation. It's called the bending equation. Is stress over, just give me a second. I just want to, that equation, stress all over Y is equal to M over I, M over I, which is equal to E all over R. If you know the material that you're looking for, this is your Young's modulus. That is, if you know the material that you are busy with, like you're dealing with timber, or you're dealing with steel, or you're dealing with that. This one is a radius of curvature. If you think about it, you're bending your curvature. If you the structure, if your the beam is in bending, it's like that. So that distance, that is your R, your radius of curvature. So we're not going to use this term a lot, but just before I say we're not going to use these terms, what we normally do, you select two of the two. It's either you're going to take this and that one. You don't use all three terms. is either you're going to take the first term, equate it to the second term, where you're going to say, okay, my stress all over y is equal to m all over I. Then you take y to that side, then stress becomes m all over I times y, which is the same equation as that equation there. So it's the same thing, to be honest with you. Or you can equate the first one and the last one, depending on the information that is given to you to calculate whatever that you're calculating. Or you can equate the second one and the third one. But for analysis, we like to use the first two and then ignore that one, unless you're given that information. What is the radius of curvature, or what is your E? Or sometimes you will be asked to calculate what is the radius of curvature. If you're given the M value, you're given the I value, and you're given the Young's modulus for that section, what is the radius of curvature for that? It's a question of manipulating the equation. So you'll use the first one and the last one. So the second one and the last one, if you asked to calculate the radius of curvature. If you asked to calculate the Young's modulus, now it depends on what information you're given. Are you given this in the stresses and you know the y's, or you given this information, or which information you can easily calculate? Then you can equate that last equation with the second one or the first one, depending on the information that is given to you. Okay, so those are the bending stresses. So I've discussed the tensile stress. What is the force in the member? Mainly this is in trusses, where you calculate the section and then you say it's in tension. So what is the cross-sectional area of that section? Then meaning you must know the cross-sectional area of that section, the area. Then you go to compressing. This is TU, CU, compression, applied compression force, and then the cross-sectional area. You know how to calculate the cross-section, okay, or area of a section. Then you've got shear. You know the V at that point, that where I'll ask you to calculate shear. What is the area of the section? You know how to calculate the areas. That's exactly what we were doing when we were calculating when we were dealing with section properties, calculating areas. Then when you come to bending stresses, now it's your applied moment divide by what? Divide by Z, or times I over Y. That is your calculating. Normally the bending stresses are like this. I'll show you this. Well, let's say you've got a cross section like this and I-beam like this. You can even see the profile of the section. The bending stress is going to be something like this. Okay, you can see the area must handle those stresses at the bottom of your beam. You've got a wider area here for those stresses. You've got a bigger area there for as you go towards the center of the section, the stresses tends to be 0. That's why you don't need an area there, a big area there around this area, because the stresses are getting smaller and smaller and smaller. So if you're calculating the stresses at this point at the top, that means you must use Y upper for this section. If you're calculating the stresses at the bottom, you must use Y lower, or you must calculate your Z upper or Z lower. So obviously to calculate Z upper, so you're going to use Y upper there. To calculate Z lower, you're going to use Z Y lower here. So that's all you're going to do. Let's take a quick example on how to calculate bending stresses. Hopefully you will find it very useful. You're given this, over 5 meters, spanning over 5 meters. And you told there that the uniformly distributed load is 25 kilonewtons per meter. For a simple supported beam like this, guys, I'm sorry to tell you that if you're gonna start by calculating reactions and draw a shear force diagram and do that to calculate your bending moment, then you're going to have a problem, a serious problem. Okay, you're going to have a problem. So to calculate a moment here, you know that the moment here is 0, the moment here is 0, and you know that your bending moment diagram is going to look like this. You just want this moment. If you want that moment, this moment m WL squared over 8, you just use that for a simple supported beam with the uniformly distributed load over the entire beam. M is equal to WL squared over 8. So my W is 25 times my length is 5 squared over 8. Then already I've got my moment, 25 times 5 squared. Sorry. Okay. 78,13 kilonewton meter. That is the moment. That is the moment that I have calculated for that section. Now, the next question, you need to calculate, you need to know what is the I value for the section that you are calculating, depending now which section is that. Remember, the bending stress is equal to M over Z. So the question is, you've got M, what is Z? That's the most important question that we must ask ourselves. Let's say you are told that you're using an I section, and then which I section is this? I'm just gonna choose any I section, guys, from the red book. Don't worry about this. It's from it's 3. I'm gonna choose this one, 305 by 102 by 25 I section. Then on that very same red book, you are told there, if you look there at the top there, sorry guys, if you look there, you given about the x-axis, you given the I-XX for that section, you given the IYY. If you go down there to somewhere, I don't know whether you can see it on my screen, you go across like this, your I-XX for that section, if it's bending about x, is 43,6 times 10 to the power 6. Sorry, 43,6 times 10 to the power 6 millimeters to the power 4. I is equal to 43,6 times 10 to the power 6 millimeter to the power 4. That is your I for that section. You also given again, if you look there at the top, you also given Z elastic and Z plastic. Don't worry about that, because at this stage you won't know which Z. There's your Z there at the bottom. You won't know which Z you must use. All you need to do, take what is the H for that section. There's H, the full height of the section. That's H. You know that H for that section, I'm looking there, is 305,1. There's H for that section. All the way from there, there's H there at the top. H. all the way down is 305,1. That is the full height of the section, h being the full height of the section. So because it's a double symmetric section, so my y lower is equal to my y upper, which is equal to 305,1 divided by 2. 305.1 divided by 2 gives me 152.55 millimeters. That is my y bar. That is my y bar for that section. So now I'm calculating z. So z is equal to I all over y. So in this case it's irrelevant which I, because the section is symmetrical, y lower and y upper are equal. But in the case where your y lower and y upper are not equal, you must know which z you are calculating. Is that right? Okay. So my I is 43,6 times 10 to the power 6. My y is 152,55. So I'm calculating z now. 43.6 exponent 6 divided by 152.55. Okay, 285,01 times 10 to the power 3 millimeters to the power 3. That is z. So stress top is equal to stress bottom. Why am I saying that? Because z top is equal to z bottom. Why is z top equal to z bottom? Because y upper and y lower are equal. Then my moment is 78,13 times 10 to the power 6. Why am I multiplying by 10 to the power 6? Remember, this is in kilonewtons. To convert it into newtons, you multiply by 1000. To convert that one into millimeters, you multiply by 1000 again. That's why I'm multiplying by 1000 to the power 3000 to the power 3 twice. So this is 10 to the power 3 times 10 to the power 3. Then 10 to the power, add the indices 6. Okay, the bases are equal, then you add the indices. Okay, so you divide that by your z. It's 285,01 times 10 to the power 3. So what is your stress? 78,13 exponent 6 divided by 285,01 exponent 3. It's 274,13 Newton per millimeter squared. Okay, these are the units. It's force over area, guys. So this is your, it's too high though, it's very high. Maybe I've chosen a smaller section just to demonstrate this example. This section is too small because that stress is very high. We shouldn't be dealing with those stresses, with so high stresses. Yeah. Okay. This is how you calculate the bending stresses. So how do you draw it? There's your I section. Remember, in this case you just draw them. This is 274,13 at the top, 274,13 at the bottom. Okay, I don't want to get into details why I'm drawing it like this. One must be negative, the other one must be positive. No, let's not go there yet. So at least I won't be expecting you guys to draw this stress. For now, don't worry about this for now. If I explain it to you further, how you come to, how do you go about draw these ones, then you'll be expected to draw it. If I don't explain it further, then don't worry about drawing the stresses. So that's how you calculate the bending stresses. I was saying to you earlier on, sometimes you will be asked to calculate something else now. Okay, something else. What is the radius of gyration? If, for example, this one. So you've got your stresses, you've got the stress, you've got the applied moment. In this case, I can further say calculate the radius of curvature. So I must give you E for this section. So it's 200 times 10 to the power 3 newtons per millimeter squared. Let's say the E value is given in that. I want you to calculate R. So out of that formula, remember the formula, stress over Y is equal to M all over I, which is equal to E all over R. So I want you to calculate this now. So meaning you must use this term. Then it's up to you whether you want to use it like this, or you want to use this term, this one, together with that one. But it should give you the same answer. You can use this term and that term, or you can use this term and this term. So if you go that route, it's up to you how you want to use it. E all over R is equal to, it's up to you, because you've got I, you've got M, you've got that, and you've got that. You've got all the information. I'm just going to use M all over I. And then across multiply. Cross multiply. And that gives me MR all over. MR is equal to, not all over, MR is equal to I E. Then R is equal to I E all over M. I value must be in millimeters, E must be in Newton millimeters, M must be in millimeters. And then I come and I don't want to start a new. Your radius will be equal to I is given then 43,6 times 10 to the power 6 times the E value. I'm giving you E value here, 200 times 10 to the power 3, and then M 78,13 times 10 to the power 6. What is the radius of curvature? Obvious it's going to be a very big radius. Obvious it's going to be a very big radius, and it's in millimeters. 43.6 times 200 exponent 3 divided by 78,13. It's 111,61 times 10 to the power 3 millimeters. That's the radius of curvature for this section. So that's how you calculate the bending stresses. So in terms of the compression stresses and the tensile stresses, it's straightforward, guys. You just take the tension force, you divide by the cross-sectional area. Take the compression force, divide by the cross-sectional area. So I hope you will enjoy the section. If you have questions, feel free to contact me, guys, anytime. I'll be able to help you where help is needed. Thank you, guys. Cheers. Bye.